G'day viewers, in this segment I'm going to talk about IP addresses and IP prefixes. So I've talked a fair bit about packets, and we know packets carry addresses and so forth, but I haven't really gone over any of the details so far of those addresses inside packets. That's what we're going to do now in this video as we take a deep dive and look at IP addresses. And as well as IP addresses, I'll also tell you about an important concept called IP prefixes, which are really blocks of addresses. And just a quick note here, what I'm going to cover is for IPv4, the version of IP which is mostly deployed in the current internet. It's going to change when we get to IP version 6 later on. So IP addresses. IPv4 uses 32-bit addresses. When we get to IPv6 later on, we'll see that IPv6 uses 128-bit addresses, a much larger address space. The reason for that is that the 32-bit address space is near exhausted. But for now, we'll just concentrate on those 32-bit IPv4 addresses. These addresses are written in what's called a dotted quad notation. They're 4 8-bit numbers separated by dots. Because, of course, the 4 8 bits, that's where the 32 bits comes from. You can see here I have binary representations where all of the bits are spelled out in the groups of A's, B's, C's and D's, each 8 bits long. And on the other side are the decimal numbers that they correspond to. So we might be able to write out a number in binary, but we're not going to want to work with it in that format. It would be tedious. Instead, we'll convert the 8 groups of bits into the decimal equivalent and write them in this dotted quad notation as 4 decimal numbers. They're going to range from 0 to 255 since they're 8 bits. Each number separated by dots. So let's do an example. Here's the example here. Now, we have this big long binary string, wow, and we want to write it in our dotted quad notation. So what's it going to be? I'm going to start at the end, and this last number, all zeros and a 1 bit, well, that's the equivalent of the decimal number 1, so there's a 1 at the end. I just know that because the 1 is in the 2 to the 0 position. Above that, all zeros, well, that's also the decimal number 0, that's not too hard. Okay, now we have to do a little bit of work for the one above it. We have a 1 bit on in the 2 to the 0 position, that's a 1. In the 2 to the 1 position, that's a 2. The 2 to the 2 position, a 4. The 2 to the 3, 8. And the 2 to the 4, 16. So if I add up all of those numbers, 16 plus 8 plus 4 plus 2 plus 1, I will get 31. So this is the binary representation of 31. And going on over here, this has the 2 to the 2 bit and the 2 to the 16 bit. Set, so when you add them up you get 18. So that's the binary representation of 18. You might be a little rusty or unfamiliar with all of this, and it can take a little while to get started, but you can usually work through binary addresses. It just takes a little getting used to. That's an IP address. I also want to tell you about this concept called an IP prefix. IP addresses are allocated in blocks called prefixes. And that's what routing in the internet is going to use. That's why we're going to talk about prefixes. Well, what is a prefix? Well, it's really just this block of IP addresses, but it's a block that's structured in a specific way. All addresses in an L-bit prefix are going to have the same top L bits. So you can see here, here's L, here's my prefix length of L. L can range, well, I guess from 0 up to 32, although commonly it will have values such as 16. Or anywhere from 8 to 24. Now, if I have the prefix length of L bits, that means that the top L bits in this number are going to have some fixed value, and the last bits here I'll just write X's here because they can take on any of the different possible binary patterns. So this means that since the top the L bits are fixed and there are 32 bits overall, we have 32 minus L bits at the end that can vary. So there are 2 to the 32 minus L addresses in an L-bit prefix. For instance, a 24-bit prefix is going to have 8 bits left over, so there are 2 to the 8 or 256 addresses in a /24 in a 24-bit prefix. These addresses, by the way, are also going to be aligned on a 2 to the power of 32 minus L boundary. So prefixes with 2 to the 16 addresses in will start on a multiple of 2 to the 16 rather than any arbitrary binary position. This is just like talking about numbers that are powers of 10 aligned on multiples of 10. Sorry, numbers that are multiples of 10. 10, 20, 30, 40 and so forth. And they start on multiples of 10 rather than 22, 32, 42 and so forth. Okay. We also want a way to write IP prefixes. How are we going to do that? We need a notation. Well, we're going to use this IP address / length notation. The address will be the lowest address in the prefix written in our familiar dotted quad notation, and the length at the end, the / length, will be just the length of the prefix in bits. So for instance, 128.13.0.0/16 means it has a 16-bit length prefix, so that means the last 32 minus 16, or 16 bits, will be free. So the addresses will range from the bottom address, which was given as part of the prefix, to the same address when I turn on all of the bottom 16 bits. So you can see when I do that, I get to 128.13.255.255. This means that a /24, and that this is how you pronounce something like this, or a /16 for instance. As I said previously, a /24 will have the last 8 bits free, so it'll have 2 to the 8 or 256 addresses. Similarly, a /32 really means one address. Let's do an example to see how all of that works. So here is a number written out in binary, except I've X'd out the last bits because they can take any value. How will we write that in our notation? Well, we have the last 8 bits are free, so the first 24 bits are fixed. So that means this is a /24 prefix. Okay, and to come up with the value, well, I'll set for the lowest address, I'll set all of the X's to 0. So we have .0, above that is 0, and above that, well, I have to do my binary to decimal conversions, but luckily I'm using the same examples as before. So you might recognize that as a 31 and an 18. So this prefix is 183100/24. Let's do another one. Okay, this other prefix that I talked about above, 128.13.0.0/16. Well, we said that the first 16 bits are fixed, the last 16 bits are free, so I'm going to write X's for them. We sort of fill them in as zeros just to write the lowest address in the prefix. Above that, I have 13. I want to write that as binary. Well, let's see. 13 in terms of powers of 2 is 8 plus 4 plus 1. So I'll turn those bits on, and I'll turn the other bits off. 1 on the 8-bit, 1 on the 4-bit, and 1 on the 1-bit, and everything else is 0. So this was 13. And I also want 128 for the top bit. It sounds a little harder, it's a bigger number, but 128 is actually a power of 2. That is 2 to the 7. So the top bit's going to go on, and all of the other bits are going to go off. And there we have it. There's the binary representation of that prefix. There's a little more terminology that goes with prefixes too that we need to know. We can talk about either more specific or less specific prefixes. More specific means that the length of the prefix is longer. That is narrowing the range of addresses because we're pinning down more of the bits at top. So a more specific prefix will have a smaller number of IP addresses. Similarly, a less specific prefix has a shorter prefix. It allows more of the bits to be free, so it will have a larger number of IP addresses. And I'm spelling this out because it's a little counterintuitive at first. But you can see on this diagram, as I go to less specific, the prefixes get shorter, but the number of addresses that can be within the prefix gets larger. Similarly, as I go to more specific, the length of the prefix gets longer, it's been more specific, but the number of addresses inside that prefix gets smaller. So that's IP prefixes. Now you know about IP prefixes. There's a little more I can tell you about IP addresses though, and I'm going to start with classful addressing, which was used historically. So we use IP prefixes today. Originally, IP addresses came in fixed size blocks. So the prefix length, if you like, was fixed and pinned down as part of the address. In particular, Class A addresses that are shown here had the first 8 bits were used for the network portion, the last 24 bits were free, and Class A addresses were identified by a leading 0, and then you could set the remaining 7 bits of the network mask to whatever value for the different Class A addresses. So you can see actually that a Class A address corresponds to a /8 since only the top 8 bits are fixed. So there are a lot of addresses in a Class A address to the 24, that's large. Similarly, if you do a little bit of work, you'll see that the Class B and Class C addresses here equivalent to our /16 and our /24 prefixes. Although, of course, the top bits are constrained in these patterns, 1, 0 and 1, 1, 0, so we can identify the class A, B, or C addresses just from looking at the top portion of the bits. Now, addresses still have these top bits that identify whether they belong to a Class A or Class B or Class C networks, but the classes themselves are ignored. If you like, the prefix notion that we use today is a generalization of these classes which is used instead. Now, instead of only being able to have /8, 16 and 24, we can have prefix lengths in between and so forth. And that's why the top bits of the address, they're left in there for compatibility, but they're ignored otherwise. There's also one important distinction for addresses that will come up as we use them in the internet is between public and private addresses. So far I've been talking about public IP addresses. So for instance 1831, here I'll use .0.1 is a public IP address. Public IP addresses are any address which is a valid destination address and can be used on the global internet. So you can send packets to that address and from that address. Well, before you can use a public IP address, you've got to get one from somewhere. You can't make it up. So they need to be allocated to you. And I'll talk about that in a minute. The problem with this allocation is they're mostly exhausted. We've almost run out of them. That's why we need IPv6. On the other hand, and this is the distinction I want to draw, there are also a small number of what are called private IP addresses. Private IP addresses are addresses that you can use freely without anyone giving them to you in your own private network. And that might be a small home network or a small company network. You can just assign these addresses to computers. You might have seen some of these addresses already. Anything in Net 10 or often home networks, for instance, use 192.168.0.0/16 as their prefix. So these are private addresses, but of course, pretty much any network, even a private network you make, you're going to want to connect it to the public internet so you can talk to all of the computers out there. To do that, you will need to get a public IP address, you'll get that from your ISP, and you'll need to use a technology called NAT to translate, network address translation, to translate between these private addresses, which are only valid within a private network, and public addresses, which can be used on the public internet. We'll get to NAT in a later segment, and I'll explain how it works. For now, you should mostly think in terms of public IP addresses. When we're talking about addresses on the open internet, that's what we mean. Well, to complete the picture, let me finally tell you where these addresses come from. The allocation of public IP addresses follows a hierarchical process. In the beginning, on the left-hand side of this diagram, all addresses belong to a body called IANA. That's the Internet Assigned Numbers Authority, something like that. And what IANA does, it owns all of the address space, just de facto. It delegates different portions of the address space to all of these regional bodies. These are called RIRs, Regional Internet Registries. And they have different names. There's ARIN is the name of the Internet Registry, the RIR that serves the US and Canada, North America, other places, maybe Antarctica, something like that. There's APNIC for the Asia Pacific. Actually, maybe they serve Antarctica. RIPE, LACNIC for Latin America, AFRINIC, and so forth. These are all regional bodies. What these bodies then do is the regional bodies then delegate IP addresses to companies in their regions. The companies apply for these IP addresses and they get them. And then finally, once your company has an IP address, it assigns those addresses to computers in its network, either its customers or in the case of an ISP, who then assign them to their computers. Or in a small enterprise, you would assign them directly to your computers. This is done with a protocol called DHCP these days, and we'll get to DHCP again in a later segment. Okay, but now you know a lot about IP addresses.